I will start to welcome you all to this virtual visit to Portugal, namely to the National Meeting of the Portuguese Mathematical Society. And once again, I thank all the speakers for accepting my invitation to participate in this parallel section of Nonlinear PDEs. I also thank the participants who chose to join us. I think all of you know that Di Benedetto, one of the most influential mathematicians working on PDEs, died recently. And this session is precisely my tribute to him and to his work. In the next 2 hours, we'll have several speakers talking about PDEs and some properties of the solutions. I think all of us will find it very interesting, and perhaps this session will give rise to future collaborations and works. Who knows? If you all agree, the scheme of our session will go as follows. The first 3 talks are of 20 minutes maximum, and then we have a last one of 40 minutes. And we save 10 minutes at the end just to make some questions or remarks or comments, okay? So we follow the order presented in the page of this national meeting, and we start with Nayan Liao, a colleague of ours working in the University of Salzburg in Austria. He's been very interested in improving regularity results for the weak solutions to several nonlinear PDEs. And that is precisely the topic of his talk entitled Moduli of Continuity for the Stefan Problem. Nayan, thank you so much for being with us. Please, the stage is yours.
Thanks for the introduction and invitation. I'm going to start the sharing the screen. So, okay. All right, so my talk today is about modulus continuity for the Stefan problem. It will be a very brief, very short talk because I only have 20 minutes at most, and so I'm not going to involve any proofs, only like brief reports of recent advances. And the starting point was the classical Stefan problem. Stefan was a physicist. Once it was a Slovenia physicist, and he considered around the year 1890 the following problem of the change of phase of material, in particular water, the melting water, ice to water, and so I'm showing you the following picture, which I took from Vicentin's book. It's a lecture notes, very nice one. And originally, this problem was solved in 1 dimension. So you have the following picture. So suppose you are given initially a portion of ice, which is here from A to S0, for example, a portion that is occupied by water. So there is an interface. Well, the face is a point for 1 space dimension, of course. So as the time goes by, the interface of the water and the ice is going to evolve. And the problem consists in finding temperature at each point of space and time and finding the curve of free boundary, the interface between the 2 phases. This was solved in 1 space dimension by Stefan in around 1890, more than 100 years ago, by integral equations. And this was, so in 1 dimension, you can use integral dimensions, and this was understood very well. But this does not generalize to a higher dimension. And there was a fundamental missing part that somehow prevent people from going to higher dimension. And this was only somehow solved much later after systematic development of functional analysis, in particular introduction of sublet spaces. So that's around the mid-page of the last century. This was first proposed by 2 Russian mathematicians. Kamin was the first one who proposed this weak formulation for Stefan problem in higher dimension, in any space dimension n. And Kamin was, I think Kamin, according to Friedman, Kamin was the first one. And Kamin was a student of Olenek. And in the later technical report by Olenek, this was also mentioned. So these are two original literatures. They were both in Russian, how to read. So the thing was, once you have bigger space of Sobolev functions, it's easier, somehow easier to find the solutions. So you can establish solution. You can find weak solution. You can find a solution in a bigger space, and it is actually a general program, a general scheme for partial differential equations, meaning partial differential equations. You find weak solutions in the weak sense. Then you have to ask yourself whether they are regular, at least continuous. For example, continuity of the solution is particularly interesting for this problem because it says the U here, the solution represents temperature. If the temperature is not continuous, it's going to be physically strange because it says across the ice-water interface, there would be a jump of temperature. This is physically nonsense. Although you can see that in the weak formulation from those two Russian papers, there was a jump for beta that is representing the energy, sort of energy. So the energy is going to increase as the temperature U increases. This makes sense. And it's going to be linear. So when U is strictly larger than 0 or strictly less than 0, this makes sense because in the state of ice, the temperature is going to be governed by the heat equation. In a state of the portion of water, the temperature is also following the heat equation, but there's a jump across the jump of energy across the interface. This was a very particular phenomenon when you have a phase change. And so the question is, now in the 1960s, people can find weak solutions. People have the existence of weak solutions. Are weak solutions regular? More particularly, are they continuous? So this is the question raised by Olenek in his technical report, this paper. This was answered by pioneering works of 4 papers. So they have shown the temperature is indeed going to be continuous, as formulated in the Olenek's paper and the Commons paper. So all these 4 papers have different characters, which I do not have time to go into detail. But a common point of all of them is the use of the George type lemma. All of them use the George type lemma. So basically, it says the strong machinery, the strong iteration of the Georgi enables one to obtain point-wise information from very weak measure information. And I mainly follow Di-Benedetto's approach, which is the most flexible one. All subsequent works, as far as I know, all use his approach. And then 2 years later, Di-Benedetto-Friedman quantified the modulus in the 82 paper of Di-Benedetto. In fact, this 84 paper of Di-Benedetto-Friedman was mainly concerned with the gradient regularity of solutions to p-parabolic systems. So they have shown that for a weak solution to parabolic p-Laplacian system, its gradient is going to be continuous, and the modulus continuity is going to be exactly this log type, double log type modulus. And this, they pointed out in a remark that this modulus is exactly the modulus in Di-Benedetto's 82 paper. So these are the connections of the 2 papers. And then you can ask whether this is optimal. So why are you so concerned with, you may ask me, why are you so concerned with the modulus continuity? Why do you stick with the modulus continuity? It was because, partially it was because this Stefan problem is going to be generating some free boundary problems. And you want to know how regular the free boundary is going to be. And this is ultimately related to the modulus continuity of the temperature of the solution. And this was achieved, such an improvement was achieved 30 years later after Di Benedetto and Friedman's paper. And this was done by Urbano and collaborators. And this was, well, I will come back to this paper later as it deals with more general setting. But for this equation, as the title shows, with a Laplacian, it improves Di Benedetto and Friedman's modulus to, in the sense that they discarded one logarithm. And also the sigma, the power sigma can be quantified by the dimension very specifically, very explicitly. So this was a great improvement in 30 years. And then you ask the same question, is it possible, is it optimal, is it sharp, is it optimal? And recently I think I could somehow improve this modulus in low space dimensions. So what I can do is in one dimension, in one space dimension, the modulus is actually a holder. There's something special happening in those space dimensions. While in two space dimension, the modulus I got is going to be a weaker, is going to be a modulus weaker than the holder modulus, but it is stronger than the logarithmic type modulus. So of course, when n is larger than or equal to 3, it goes back to the previous slide by the result of Urbano and other collaborators. So this is for the original problem of Olenek. Now people can also consider the effect of P-Laplacian type diffusion. This is a very natural question. How about replacing your diffusion part by a more general nonlinear operator like P-Laplacian? This was first attacked by Urbano more than 20 years ago, and he handled the case P larger than 2, and later the P less than 2 case was attacked by Urbano and Eureka, and more recently there was an interesting paper of Keith and Lee, who studied the stability of the continuity of the solution as P goes to 2 from below. So this kind of stability issue was always there when people deal with the parabolic P-Laplacian type thing, when it comes to parabolic and when you have P-Laplacian operator. In general, well, for some cases, for most cases, I would say P are not going to be stable as the method shows, but stability has to be studied separately. Somehow was some interesting issue, but it's not out of the scope of this talk. So all of these papers are concerned with the continuity result of this weak solution to this more general Stefan problem involving P-Laplacian operator. How about the modulus? The modulus was given in the same paper of this ARMA paper. So they established the modulus of logarithmic type for all P larger than or equal to 2. So this is very general, and sigma, the power sigma, can be quantified explicitly by the number n and p. So this is a very sharp result. Then how about P less than 2? P less than 2, I found we can do the same thing, or similar thing, for at least for P larger than a certain critical number. And this number 2n over n plus 1 is known as a critical number in the parabolic theory of P-Laplacian. And this range is called supercritical singular range. So in this range, I found you still can quantify the same type of modulus, logarithmic type, and sigma is again quantified by n and p explicitly, at least for this supercritical range. Okay, next is the boundary regularity. This is also a natural question of PDE. When you have interior, do you have the same thing on the boundary? And the first question is about Dirichlet data. So you are giving a boundary value, G, which possesses certain smoothness. And the initial data is not going to play a role here because I'm only concerned with the side boundary, the lateral boundary regularity. So you ask yourself, is the wake solution going to be continuous up to the boundary and continuously taking, it's going to continuously take the G value of the boundary given if the G is smooth enough. And this was the first literature about this was by Zimmer. This is one of the 4 papers in one of the previous slides I showed you. So as I said, all of the 4 papers in the 80s have different characters. And the Zimmer's character was, well, it was more or less qualitative. He does not give a quantitative estimate of modulus continuity, but still his result is very interesting because he is giving a sharp result because he is concerned with a Wiener criterion on a side boundary. And if you project your parabolic operator to the bottom, to the elliptic case, and you project your cylinder to the base, and you end up with the Wiener criterion for Laplacian. So this is somehow sharp for this kind of solution, but it does not have modulus. The Benedetto was able to quantify a modulus of log-log type, and so he pushed his interior modulus to the boundary under certain conditions of the boundary. See, I used the exterior cone conditions, but his condition is more general, which I do not want to specify here because it's very technical. I want to avoid, but it's general enough to have exterior cone condition. For the P-Laplacian case, the same modulus was achieved by Urbano and other collaborators a few years ago, and then the natural question is, can we achieve a single log type modulus? And this was realized recently, and under the same, more or less the same general conditions on the boundary, the geometry of the boundary data, I can improve this modulus to a single logarithmic type. This is a recent preprint. In the same preprint, I can deal with the Neumann problem. And Neumann problem was not dealt with before. And I found the logarithmic type modulus still holds for Neumann problem. You're giving Neumann conditions. But see here, the result for the Dirichlet was for all p larger than or equal to 2. So for P-Laplacian, for p larger than or equal to 2, it's going to work, this modulus. But for Neumann data, I'm not able to deal with general P-Laplacian, but a regular P-Laplacian, a regular Laplacian is something I can deal with. There was something, I feel like there was something fundamental missing about the George classes. So under reasonable conditions on the boundary and the Neumann data, one can achieve the same type of modulus as in the interior for the standard Stefan problem. And that's the end of my talk. Thank you for listening.
Okay, thank you. We will go to the next speaker of today. Okay, so our questions and remarks, we save them to the end of our section. session. The next speaker is Nicolau Diel, from Instituto Federal de Educação, Ciência e Tecnologia de Rio Grande do Sul, Brazil. He has several works concerning nonlinear PDEs and is quite committed to the study of the porous medium equation. His today's talk concerns global solvability for porous medium equations with advection. Nicolau, thank you, and feel free to start whenever you're ready.
Thank you, Eureka, for the invitation and the introduction. I will speak about global solvability for porous medium equation with advection. This work is jointly Paulo Zingano and Lucinéia Fabris. And okay. In this work, we consider the porous medium equation with an extra term, this divergent of the flux F, which is would represent the divergency in the problem. We take initial state in L1 and bounded. We work in whole space Rn. Our advection flux is has the general form B. There are two velocity fields, B and C, and our advection flux is B times U plus C times U. Okay, these velocity fields are continuous, and we can take the these particular partial derivatives to compute the divergency, the divergence, and for the velocity field C, we consider these two properties, 2 and 3. The property 2 is called Semi-Dissipative Condition, and the property 3 is a bound to the norm, the Euclidean norm of this vector C. And sorry, this 2 is a misprint, is the Euclidean vector, the Euclidean norm of the vector B2. And the condition 4 is a growth condition. And what is the difference of the velocity field C and B? Well, when the velocity field B is 0, then we have the semi-dissipative condition, and the problem has the same behavior as in the case when you have F equals 0. The LQ norms decay in time, and then we can prove that we can prove LQ, LP estimates, and we can iterate this and let Q, for example, go to infinity, and we prove that the subnorm decay in time, and we had proven splicity rates of decay in this paper in 2020. But when this condition 5 does not hold, you don't have that the LQ norms are decreasing, and you can have and you cannot prove in the same way that the LQ and LP estimates. Let's illustrate this difficulty. If we take the velocity field B in this special way, and and compute the divergent, our equation 1 becomes 6. And this beta, when this beta is large, in the case where k is large, this term acts like a source term. In the regions where this beta is large, it's possible to have blow up at some finite time, like in Fujita papers or something like this. We did some simulations, and we in this figure represent 18-fold increase in solution. And if we modify this velocity field B, we can get a 18,000-fold increase, taking this B at the end of this slide. And what can avoid this blow up? There are two elements, the diffusion and the property that L1 norm is decreasing. It's the L1 norm, it's the only norm that we can prove this property. For Q non-equal 1, it's not possible to show that LQ norm in general decrease. It's our first result. The L1 norm is bounded by the L1 norm of initial profile. And in view of this constraint, any substantial growth of the solution in magnitude will lead to the development of high-frequency structures. And then the diffusion acts very efficiently to dissipate these high-frequency structures. And there is a competition between the diffusive and the advective term. Our strategy is control the LQ norms, but is different of the case where you don't have advection. We start by proving a lemma, which gives us this energy inequality. And in the sequel, we prove a punctual estimate that say LQ norms at the point, at a specific point is bounded, since the derivative of LQ norms is positive. So is positive, sorry, is non-negative. Then our norm, LQ norm, is non-increasing, or the LQ norm is bounded. So we can bound the LQ norm with a suitable LP estimate. We take P and sigma satisfying 8 and 9, right? Sigma is fixed and P is fixed later. And then we can prove that LQ norm, the supremum over the interval 0t of LQ norm, which we represent by this special U, is bounded by the initial state LQ norm, or this expression here, which is a constant times special B in a certain power times basically LP, the LP norm of our solution, right? In some power. Here, this special B is the supremum over the interval 0t of our B, our function B, which appear in the growth condition to the velocity field B, right? Then the next step is to take Q equal P times sigma in a power m, where m is a natural number, and then iterate this result and let m go to infinity. Then we have a subnorm estimate. The subnorm estimate in the supremum of in the interval 0t of the subnorm estimate is bounded by a constant times the initial profile L infinite norm, or this special B in a certain power, times the UP. Then to guarantee global solvability, we need to guarantee that this term UP is finite. If we can take P equal 1, so it's done, because the L1 norm is decreasing and bounded by the initial state L1 norm. It is the theorem 1. All solutions are globally defined since K is less than K star. And K star is alpha plus 1 over n. In this case, we can take P equal 1. Remember 8. From this condition 8, if K is less than K star, we can take P equal 1. And then all solutions are globally defined for all initial states in L1 and L infinity. To the complementary case, K greater than K star or K equal K star, we need to require something smallness condition to the initial profile. In the first case, K equal K star, we need to put L1 norm of the initial condition is small. And in our paper, we describe this constant. We have a explicit expression to delta, right? Depending only on n, the dimension n, alpha, and k. And to the second case, we need a smallness condition for the initial profile L infinity norm. Well, the idea of the proof is to bound this special UP here. How can we, how can we do this? We take our energy inequality and we derive this new inequality. And the idea is to absorb this red term in the blue term, right? And it is possible in each case, since the condition 1 and 2 are satisfied in each case. And if we can do this, we can conclude that LQ norm are decreasing or non-increasing. And then this specific LQ norm is of the solution is bounded by the initial state. And then we can apply again our Supernorm estimate to bound this term. And then we have a bound to the subnorm of our solution. So we have global existence. Well, it's the end of my talk. I hope it's okay. There are some reference of our paper, and thanks.
Hi, Nicolau, thank you. Well, if someone wants to just put something in the Q&A button for some questions or remarks to be answered after all the presentations, please feel free to do it. We now will restart with the next speaker. The next speaker is Sergei Shmarev from Universidad de Oviedo in Spain. And for sure, all of us know several of his works, if not all of them. And we are willing to hear him talking about one of the recent works he has done concerning nonlinear parabolic equations with the nonlinear structure depending on the solution. So we are talking about non-local situations, problems, equations. So dear Sergei, thank you so much for joining us. And please, you can start your presentation.
Okay, thank you.
Thank you.
Okay, good afternoon, everybody. So thank you for the nice presentation. Well, I'll talk about a class of non-local parabolic equations with a specific nonlinear structure. The structure is defined by the solution itself. And the original results I will present were obtained in collaboration with Stanislav Antontsev and Ivan Kuznetsov. Okay, so this is the class of equations I'm interested in. So this is the equation of the P-Laplace structure, but P is not a constant. P is not a function, a given function of the variables. P is a functional, or P is a function whose argument is a function of the unknown solution. So we consider this class of functionals. So P has as an argument the integral over the space domain. So in fact, what we have here is a function of T, but the function is unknown. This is the first group of equations. The second group has the same structure, but here E depends on the integral of some power of the gradient. And this type of argument is chosen just for the sake of presentation. This is a question of convenience, because actually everything extends to the case when you have at the argument of P a linear function of U, of suitable structure, of course. Well, this is an exotic statement, and actually, when we started this activity, we were thinking about the system of equations, but that's what we have for the moment, and that's what I'm going to present. Well, several words about the situations where equations of this type may appear. Well, the first and very well-known and well-studied problem is a problem of processing of digital images. So assume that you are given some image, a distorted image, in black and white. So U is a function whose values belong to the interval 0, 1. This is a scale of gray. So you look for the function U, which is not too far from the distorted image, but in some sense is better. So you try to eliminate the noise. And you minimize this function. Well, if you apply the method of gradient descent, you will arrive at the parabolic equation. So the question, how to choose this function rho? You want to enhance those parts of the image where you have big gradient, which means that you have the edge of some image detail. You move from a point, the gradient is high, which means that you skip from one level line to the other level line. And if this difference is big, this means that you are at the edge. If you move along the level line, then the gradient doesn't change, or the changes are very small. So the possibility to realize this idea is the following. You may choose for rho this function, or this one, both were analyzed in the literature many years ago, or this one. And this is exactly the situation I want to talk about, because here the power P depends on the argument S. But this problem, when this model was proposed, this problem turned out to be too complicated for the complete analysis. So the polyadditive solution, you may take for P the function whose argument is defined by the initial distorted image. So if you follow the idea that the result will not be too far from the initial image, you can try to solve this problem. And this leads to the well-studied class of equations with variable or non-standard growth. Okay? But this is not the problem I'm interested in. Well, another situation. You may, and this is the model which was studied and advocated 3 years ago, 4 years ago, similar functional as before, the purification of the digital image, where the function rho is taken in this form. This is a two-dimensional model, so the vectors zeta and zeta t are the tangent and the tangent, normal and the tangent direction to the level line. The level line, if your function u is smooth, is defined by the gradient. So in fact, you're talking about this model. Okay? This is another situation when the nonlinear structure or the nonlinearity is completely defined by the solution, which is unknown. Well, another class of, or another example of such a situation is the celebrated thermistor problem. So this is a model of the process of an electric conductor where the conductivity depends on the temperature. So you have the electric current in a conductor, and according to the properties, the conductivity properties of this conductor depend on the temperature. And in turn, according to the Joule law, the conductivity as a temperature is defined or is influenced by the current. So if you model this process, you have to solve two equations. The first one is the equation for the potential of the electric field, where the conductivity is a function which is defined by the temperature. And the second equation is the heat equation, well, the stationary version of the heat equation, so the Poisson equation, where the right-hand side depends on the potential. Okay? And now, if you know how to solve the second equation, if you have the green function, for example, well, this is a simplified example. If you have the green function, then we can express theta through the convolution with the green function, and after substitution into the first equation, you have exactly the equation I'm going to talk about. Okay. Another model, the model of thermoreological fluids, which was, well, this problem was solved by Anton and Rodriguez 15 years ago. And this is a model which includes the Navier-Stokes equation, the system of modified Navier-Stokes equation, where the parameters are not constants, but functions of the temperature. The rheology of this fluid is defined or depends on the temperature. And for the temperature, you have to solve an independent equation, which involves the temperature convection law. Okay. Another example, also the class of fluids which is well studied, electrorheological fluids. Here, the rheology of the fluid depends on the electric and magnetic field applied to this fluid. And the resulting system of equations is similar to this one, to the thermoreological fluids. If you somehow manage to solve this system and you can express one of the unknowns, after substitution into the rest of the equations, you obtain the equation of the structure I'm going to talk about. Okay? Well, this is just an explanation why this object seems to be interesting. And now about one more example, the model of spreading of a biological population. Well, in this case, P, the rate which defines the rate of expansion of a colony of bacteria, for example, this P is a function of the total number of individuals in this colony. Okay? This is another example. And now about the known results in this way. Well, all known results refer, except one, refer to the stationary case. And let me outline right in the beginning that the main difficulty here is that you have to solve an equation in the space which is undefined. The space should be defined together with the solution. So in this case, you cannot interpret the equation as a duality relation in a Banach space. The Banach space is not given. You have to define this space together with the function u with the solution. And this is the main problem. Well, the first example, or the first solution of this problem was published in 2010, Andrianov and collaborators. They studied the P of u Laplacian and the coupled problem. The coupled problems can be interpreted as a non-local equation because you have a system. If you solve one of the two equations in this system and substitute into the first one, you have the non-local equations of the type I'm talking about. And their idea was the following. Since you don't know the space, but you know that P is greater than 1, then you know that the gradients, or the equation of this structure, the gradients will be at least in L1. This is guaranteed. So with this information, you can apply Young measures, define the solution in certain sense, and then try to improve its properties. Well, this strategy worked. The next example. This is a work by Michel Chipot and Hermenegildo Borges de Oliveira. The results about the P of u Laplacian problem. They also studied a non-local problem, but their strategy was different. They established the estimates on these nonlinear combinations of the gradients, used the almost everywhere convergence of the exponents, and then proved a very fine lemma about the possibility to pass to the limit in this sequence and establish the result in the right function space. And then their ideas were extended to the parabolic equations in the non-local, with non-local exponent P, in a very recent paper published this year. But in this paper, the time derivative was approximated by the finite difference relations. So in fact, the authors, well, in certain sense, repeated the arguments which were already stated in the elliptic case, in the stationary case, and then would answer the question about the convergence of the time derivative too. Okay. Now, the time is running, so let me very briefly present the results obtained. So first, we know how to obtain the existence locally or globally in time. First, we know how to prove the uniqueness, and we have the result about the complete vanishing of the solution in a finite time. But our results are confined to the case when P, the function P, which non-locally depends on the solution, is squeezed between 1 and 2. The fast diffusion case, only fast diffusion case. Well, the definition of the solution. Well, and where this condition, the restriction to the fast diffusion case, where this condition becomes important. Here, in the definition, you may see that we don't use information about the function P. The solution belongs to this space, L infinity in time, and W naught 1, 2 in the space variables. So we use minimally possible information about this exponent. And this is a result. What we need, smooth boundary, C2, smooth initial data, W1, 2, one times differentiable function P, and this restriction on the exponent P. In this case, we know how to prove that the problem has at least one solution with these regularity properties. You may see that the properties are very strong. The gradient is bounded, time derivative in L2, and the second derivatives to the power P of U are integrable. So this is a very strong solution. Well, the proof, this is, well, let me skip almost to the end. So we regularize the equation, consider this problem, and then construct the sequence of Galerkin's approximations. The proof of the convergence is based on the three main estimates. First is obtained by multiplication by U, second by the Laplacian of U, and the third by the time derivative of U. Well, let me skip all these technicalities, but almost at every stage of the selection of the convergent sequences, we use the fact that P is strictly less than 2. In this case, we have some extra integrability. In this case, for example, which simplifies significantly the selection of these sequences. Also, we have pointwise convergence of the sequence of the exponents. Okay. Well, to pass through the limit in epsilon and to arrive at the solution of the degenerate problem, singular problem, this is a technical thing, basically the same. Now, 2 words about the uniqueness. We can prove the uniqueness, and this is not a trivial thing because, in fact, we have to compare the solutions of 2 different equations, because to every U, we have its own exponent P. Mm-hmm. If we have 2 different solutions, these P's will be different. Nonetheless, since we have an extra regularity of the solution, it belongs to W01T, not P2, this comparison is possible. Okay? And in the elliptic case, there is no uniqueness, it's proven. Well, no time, so I will skip this. Finally, we can prove vanishing in a finite time. So every solution must vanish in a finite time. Well, also, this is a modification of some known methods because this P, the non-local exponent, brings in some specific difficulties, but well, it can be handled, so it's okay. Well, the results can be extended to the cases when you have a more general form of this non-local argument of the exponent P, when you have something on the right-hand side, which depends, for example, on the terms of this form. Also, you have the same results And as for the case when you have the dependence on the gradient, you have to impose more restrictive conditions on the values of P, admissible values of this function P, and admissible values of the integrability exponent alpha. But everything is fine if P is, well, the derivative of P is close to zero, so it's almost a constant, or these parameters are sufficiently small beta, or small variation of the exponent. And also we have the uniqueness, but we have to claim impose some additional condition on the integrability parameter alpha. Okay, this was published in 3 works quite recently, in the last 2 years. And thank you very much for your attention.
Thank you, Sergey. Nice talk. It's always nice to hear some physical meanings of the equations that we usually work with. And so we go to our last speaker, Maria Micaela Porzio from Università di Roma. Her works go back to the 90s, when results concerning L-infinity estimates for the generating singular equations were obtained. Her interests cover diverse topics such as regularity, existence, uniqueness of solutions both to elliptic and parabolic equations. Today, we'll be hearing her talking about smoothing or non-smoothing properties for some nonlinear evolutionary PDEs. Dear Maria Micaela, it is a pleasure to have you with us today. So I'm not seeing you right now, but I think.
Thanks.
Okay. So feel free to start whenever you're ready.
I try to. Okay. You see?
Yes.
Perfect. Thanks a lot for the invitation. I am only sorry that not to be in Portugal, in your wonderful country, but maybe a little time. It's a pleasure to dedicate this talk to Emanuele Di Benedetto, because I have had the pleasure to know him a lot of time ago when I was a student. And he came to Rome for a courses, and he teach a lot. He explained Hilbert continuity for P. Laplacian with a lot of technicality, but this first impact helped me a lot. And then I came to Chicago, to the Northwestern, when he was for 1 year. And he taught me a lot of things, and also the enthusiasm to study regularity. And so I am very happy to be here in this occasion. And my talk today is on this. Oh, I'm sorry that I am. Okay. I will speak about this problem where omega will be an open-bounded set of Rn. Capital T can be a finite or plus infinity, what do you prefer? On the operator, I assume that it is a Lerelian's operator with row 2. This means that you have discursiveness with this exponent is equal to 2, a control from above, and this monotony condition. And on the data, I assume that they are in Lebesgue space, and they can be also very irregular, because also the case of only L1 initial datum or forcing term F L1 is possible, is allowed. And this problem was studied a lot, and also because it is a natural nonlinear version of the heat equation, or better, of the heat equation with a forcing term. And in this model is included also all the linear slide modification of the heat equation. Obviously, you have to assume on this matrix that is bounded and that satisfies this ellipticity condition. And the study of this problem starts more or less, and there are a lot of results about this problem. And I think it's really difficult to give a complete references about this problem, but for sure I forgot something. I'm sorry for this. And I think that one of the, for sure, pioneer work is the paper of Nash, where he proved the continuity of the solution in the linear case. But then there are milestones like the paper of Moser, of Aronson and Serrin, a lot of beautiful results of the Russian school. And, but the study on this equation starting from this period, but is more or less continuous in time because we have a lot of results also later in the 80s with a lot of paper also of the Italian school, Boccardo, Di Benedetto, but also of other people, Galluet, Herrero. Lyon's square means father and son, Murat, Pigné, Vasquez, Veron, but also more recently papers of Dall'Aglio Orsina, Cipriani, Grillo, Grenon, also the from Naples, Mercaldo, Mingione, Porretta. I also have worked a lot on this problem, and these are some of my papers about this, problem. I will use the notation to write in blue the paper from which I will describe some result later. And I think that after this presentation, you can think that it's something crazy to write another paper on this subject, because more or less you know everything. But it is not the case. It is not so crazy, because I will show you new results that were not known, or better, that in a certain way were not known in full, their full generality, or in the deeper comprehension of what really happens. And the papers from which I will speak in this talk are this last one. And which is the starting point that says me that something was not known. Consider the particular case of the heat equation, and consider the case when you don't have a reaction term. All people, I think, know very well this problem, and is, I think, very clear that if U0, if the initial datum is bounded, that the solution is bounded, and is also very easy to prove. But the heat equation has a very strong regularizing effect, because the solution became immediately bounded also if the initial datum is not bounded. It is sufficient that it is in L-bag where you want, also only in L1, and the solution immediately became bounded and satisfied an estimate that is called in literature ultra-contractive estimate or decay estimate of this type, that, as you can see, it depends only on the initial datum and a power of t that depends only on the dimension and on the summability of the initial datum. And this estimate is true for every omega, also unbounded Rn. This estimate is true independently of how is the set. But if omega has finite measure, the decay is a faster decay, because here it appears an exponential where sigma depends on the size of omega and disappears when this measure goes to infinity. And this behavior of this solution of the heat equation remains true exactly the same also estimate if you do a little change in the equation, if you put here something that is bounded. Again, you have that if the initial datum is bounded, the solution is bounded, but surprising, it was an old result of Veron. He proved that the solution became immediately bounded and satisfied exactly the same decay of the heat equation. He was able to prove this result using the semi-group theory, but he cannot have here a dependence of time. But this result, after more or less 20 years, was proved by Cipriani Grillo also with a dependence of t. He used a different technique using Sobolev logarithmic inequality. And he proves that if U0 is sufficiently regular, he needs this condition to have solution in the energy space, substantially solution with have the gradient in L2, then the solution became bounded, but has exactly the same decay of the heat equation. Indeed, the result can be generalized also to the case of less regular initial datum. It is sufficient to have U0 also in L1, it doesn't matter. The solution became immediately bounded, but when omega has a finite measure, you have also an exponential decay. This means that this estimate is not a peculiarity of the heat equation because it remains true also in this more general setting. But now what happens in our case, in the Lerelian's operator with GROW2? Also in this case, it is possible, it is a very easy exercise to prove that for bounded initial datum, you have bounded solution. But again, Cipriani Grillo proved that, okay, also if U0 is not bounded, if it is in L2 or better, the solution became bounded and satisfied exactly the same decay of the heat equation. This was something that surprised a lot these two mathematicians because they didn't expect exactly the same estimate. And what is possible is also to extend this result also for less regular initial datum, and also to prove that also the exponential decay appears as soon as omega has finite measure. So, surprisingly, also this nonlinear problem has exactly the same strong regularizing property of the heat equation and satisfies exactly the same regularity, the same estimate of the heat equation. And when I proved this result, I was also interested to understand why you have exactly the same estimate, because I think that this was interesting to understand. And the method that I've used that is different from the other proof in a certain way explain why. And I show you which is this result. To prove this result, I use a function that is very well known in the context of regularity. It is the test function of the Giorgi. And also this morning, Urbano speaks about this kind of test function when U is positive. Is the test function that with also he say use the cutoff function, but that he used to prove the Cacciopoli inequality. So this is the function gk of u, and the result is the following. Imagine to have a function u that also can solve anything, only a function such that gk of u satisfies this integral inequality, where the exponent r, b, and q are related by this algebraic condition, and assume also to have this other inequality. If you have a function u that satisfies these inequalities, then this theorem says that, okay, this function became bounded. Not only, but satisfy this estimate, that is a decay estimate, because this exponent H0 and H1 are positive exponent. And I can give you also the formula of this exponent. And the formula, as you can see, I can put only what I have, that are the exponent in this integral inequality. And these exponents are positive because this algebraic condition imply the positiveness of this exponent. And this result is true for every omega, bounded, Rn, what you prefer. But if you are in the particular case when omega has finite measure, if this exponent, look here, there is R and here is B and Q, if they are suitably related, then I have there is a faster decay. Which kind of faster decay? If B is equal to R, we have an exponential decay where sigma depends on the measure. And this dependence says that if the measure of omega goes to infinity, this exponential disappears. And if B, if is to be equal to R, is bigger than R, Then again, I have a faster decay, but of a different type. See here, we don't have an exponential, but a power that is given by the previous number, the previous exponent, plus something that is positive, because B is bigger than R. Moreover, this is a particular kind of bound that is called in literature universal bound. Universal because this constant C does not depend on U0. So these are decay estimates that are not influenced on the size of U0, that in the application will be the initial datum. So using this result in a certain way explains why we have the same estimate in the case of the heat equation and in the case of the more general nonlinear setting, because this result says, okay, but if you have the same integral inequalities, if two solutions of something satisfy the same integral inequality, applying this result, you obtain the same decay estimate. And this is exactly what happens in the case of the heat equation or in the case of the Lerelions operator with growth 2. And with these integral inequalities, we know it's not so amazing to find regularity by integral inequalities, but this method, this results seems to work well because he helps to obtain a lot of very well-known results together with new. And in the known result, this algebraic condition became the sharp condition to have decay estimate. And also the formula became sharp formula. So I don't know, but maybe at least in some cases, they are sharp. And sharp because we have countersamples. And for example, it works well if to prove decay estimate for this degenerate problem, when the degeneracy exponent is not too large, but work well in other well-known problem. For example, in the previous talk of Nicolaou, he speak about the decay of the porous media equation. Here, this work also in this case. In this case, a lot of people have worked a lot the regularity of this problem. I hope not forget nobody in this result. I have written the paper that I know on this subject. Somebody have proved this regularity with omega bounded or bounded. Putting together this result, you have this interesting result that says that if you have a solution of the porous media equation, also if U0 is only in L1 or in LR0, you have that the solution became immediately bounded and satisfy this estimate. Moreover, if omega is finite measure, what happens is that you have a faster decay and you have a universal bound because this constant does not depend on U0. And this strong regularizing effect appears also for the fast diffusion that formally seems the same equation, but is completely different because now the problem is not degenerate but singular. And this difference appears also in this result because to have this strong regularizing effect, you need that the coefficient has to be not too small. He has to be bigger than this quantity that depends on how regular is the initial datum. And in this case, you don't have universal bound. This regularization happens also for the Laplacian. In the degenerate case, we have also universal bound. In the singular case, as also Nayan observed, we need for the Laplacian a restriction to have on the degeneracy to have this improvement of regularity. Notice that for R0 equal to 1, this is exactly the exponent that appears in the previous talk. And also this condition, as proved by Di Benedetto, is a sharp condition because it's possible to construct, to see, to show. Di Benedetto also explicitly found a solution that does not regularize when P does not satisfy this the inequality. And also applying this result, you can prove new result, for example, for the doubly nonlinear equation. In the double nonlinear equation, what was known that is that in this case, where the coefficient here are M and P satisfy this condition, you have a strong regularizing effect. Notice that this exponent in the particular case of P Laplacian of porous media became exactly the previous exponent. And also in the degenerate case, there is this nice paper of Bonforte and Grillo where they proved that again a strong regularizing effect appears. But what is possible simply using integral inequalities is to prove that the result of the L infinity regularization appears as soon as you have this condition. In this condition, you have together the case of the degenerate case and the singular case. And this condition became exactly the sharp condition for the P Laplacian when m is equal to 1, and so this term disappears, or when P is equal to 2, and so this problem became the porous media or the fast diffusion equation. So anyway, and also using the case of the result when omega has a finite measure, you can see that you have a faster decay in this particular case that correspond to the algebraic condition B equal to R or B bigger than R. Anyway, here there is the reference is the paper where are taken the previous results. But now come back to our problem. What changed now is that we have a reaction term here in the right-hand side, and we want to understand what happens. What happens in which sense? I want to see which is the difference in the behavior of the solution when a reaction term is present. And for example, what happens when F is bounded and U0 is bounded or is less regular? Obviously, we have a lot of results in literature. For example, what is well known is that if F is bounded or it is sufficient that F have satisfied this condition that often is called Aronson-Ansari condition, but just appears in some previous paper of the Russian school. If this condition is true, then if U0 is bounded, the solution became bounded and satisfy this an estimate that depends only on the data. The solution that belongs to the energy space. It is also known that once that you have an infinity regularity, this is the starting point then to have Elder continuity. So this talk is devoted to the L infinity regularization because also, but then you can prove a lot of further regularity. Anyway, this result was just known in some particular case, linear case, in some result of the Russian school, but also of other people. And if you, I summarize here what I have written in the previous slides. So U sufficiently regular in the energy space, so gradient in L2 substantially. U0 bounded. If F is sufficiently good, then the solution is bounded. Notice that this condition says that if R is large, Q can be not so large and vice versa. For example, if you put here R equal to plus infinity, this condition became this condition, Q bigger than N over 2. That is the condition known in the elliptic case, if you consider the stationary problem, to have bounded solution. And I write explicitly this condition because I will need this in some slide that I will show you later. Anyway, if I want to draw this result, in this picture, I want to put everything in the square. So instead to use Q and R, I use 1 over Q and 1 over R. So this, if the exponent are in this triangle, then the solution became immediately bounded. But now I think that a natural question is, okay, but if U0 is not bounded, for example, if U0 is only in L1, what happens to this regularity result? We know that if U0 is in L1, in the particular case that F is 0, the solution became bounded. But in this more general framework, what is the result? in literature, or the previous result has a local nature. What means a local nature? Local nature means that if U0 is in L1, or also if you don't have any information on the initial datum, what happens is that all the generalized solutions are locally bounded. But what means in the classical theory generalized solution? Generalized solution means solutions that are sufficiently regular because have locally the gradient L2 and also have this regularity, and that are distributional solutions. So I think that now a question is, okay, but if U0 is only in L1, are we sure that our solution are generalized solution? That you have the gradient L2, because it's a strong regularity to ask to a solution. And because if you don't have this regularity, we don't know if the solution is bounded. And surprisingly, I didn't find an answer to this question. And so this, I am a curious person, so I try to see what happened. And to see if it is possible to prove that also if U0 is only in L1, you can recover some regularity and we can arrive to L infinity regularity or not. And the other question related to this question is the following. We have seen that if you don't have a reaction term, the solution not only became bounded, but satisfies this decay estimate. This is called decay estimate because for t that became larger, if you consider, for example, capital T plus infinity, so if you consider a global problem, global solution, this estimate says that the solution for T large go to 0, tends to 0 in the L infinity norm. That is a very strong convergence. So now it will be nice to understand, okay, but if you have F not 0, which is the asymptotic behavior of the solution, which is the regularity and which is the behavior in time? And this question was just open in the linear case. If you do a slight change in the heat equation, I have not found, maybe there are, I don't know, but I haven't found a description, a fine description of the asymptotic behavior of the solution. But now I think that you understand that you can have a lot of other open problems. For example, what happens if F does not satisfy the Aronson concerning condition, if it is less regular? What we have, what is the regularity? Which is the asymptotic behavior? And okay, obviously I can put another question, but if I put too much question, I didn't answer. So I try to answer to something. The first result is the following. If U0 is where you want in Lebesgue space, also only in L1, if F satisfies the Aronson necessary condition, then the solution became immediately bounded. Substantially, the same that happens for F equal to 0 remains true also for F satisfies this regularity property. But it's also possible to prove an estimate. It is also possible to prove this other regularity that substantially says that your solution is a generalized solution. There exists a generalized solution. But differently from the classical theory that need to prove that you have generalized solution to prove L infinity, I do the contrary. I prove the L infinity regularity, and using this regularity, I will be able to prove this regularity of the gradient. And also it's possible to prove this estimate, this L infinity estimate, where, as you see, you appears exactly the term of the previous decay estimate when F is equal to 0. Notice that this estimate is a sort of continuous, have a continuous dependence on F, and if F is equal to 0, this became exactly the previous known estimate, decay estimate. And also it's possible to estimate the gradient. So these results say, okay, doesn't matter where, how regular is the initial datum, in a certain way, the equation forget what happens at t equal to 0, because immediately recover the boundness as soon as F is regular. Okay, so we have solved the problem of the regularity when we are in this triangle. But now what happens if we are here in the other part of the square, if the Aronson-Essary condition is not satisfied? What is just known in literature? In literature, there is this old result that I proved with Lucio Boccardo and Ana Primo of the Autónoma of Madrid, where we prove that if U0 is bounded or sufficiently regular, it is not so necessary del infinity, but not L1, to be clear, then if F has his summability coefficient in this part of the square, then the solution became immediately in the energy space. So the solution have the gradient in L2 and also have more regularity, more summability properties where P and P0 are continuous function. I will write you the formula only for curiosity, but what is interesting is this function is a continuous function in P, in R, Q, and N. And coming from this zone to the Aronson-Essary zone, this exponent became plus infinity. So the regularity moves in a continuous way, passing from Aronson-Essary to this other part of the square. And what happens here? Also here, there is, in this paper with Lucio and Ana Primo, we proved that again we have a further summability regularity depending in a continuous way on the summability on F. The gradient is no more in L2, but also in this case, coming from this zone to this other, this exponent delta became 2. So again, the regularity of U on the gradient moves in a continuous way in this square. But in this result, we need that U0 is regular. So what happens if U0 is not regular enough? These are the formula if you want to see, and also something more is possible to prove also this more regularity. But anyway, what we can say if U0 is only in L1, our proof doesn't work. And but it's possible to answer to this question. What happens is the same that happens in the case of Aronson-Essary. The solution immediately in this part of the square recover the same regularity that would have when U0 is bounded. Immediately it became in the energy space and immediately recovered the same summability result that we know, that we have described before. And what happens here? I imagine that now you have the idea of the result. The result is exactly what you suppose. Also in this other zone, the solution immediately recovered the same regularity and also its gradient that would have when U0 is bounded. In other words, it doesn't matter how regular or not regular is the initial datum. If you have a reaction term, the solution immediately forget this not regularity of the initial datum and immediately reach the regularity of the solution that takes bounded initial datum. So in a certain way, the previous question about the regularity is more or less solved. But remember that we want to also understand which is the asymptotic behavior of the solution. And to understand what we can expect when F is not 0, I think that we have to understand better what happens when F is equal to 0. And to understand better, as I use with my student, I prefer to start with easy case. The easier case is to consider the linear case, a slight modification of the heat equation to put, for example, only dependence on X. How can interpret this result? In this case, consider the stationary problem associated to the parabolic problem. In this case, the solution of the stationary problem is the null solution, is the 0 solution. So to say that the solution of the evolution problems go to 0 is the same to say that the solution tends to the solution of the elliptic stationary problem associated to the parabolic problem. So not only, but you can also estimate the difference of the solution because this estimate can be written also in this way, because the solution of the elliptic problem is 0. So to say this or to say this other inequality is the same, are both true. In other words, the difference of the solution of the parabolic problem minus the solution of the elliptic problem go to zero in the infinity norm. If we think to this result in this way, this suggests a result that we have to see if it is true. Which is the result that is suggested by this interpretation? Is to say, wow, is it true that if you consider our nonlinear problem, at least in the easy case where f depends only on x, and you consider the associated stationary problem, when if you want an infinity decay, you need to assume that both the solutions are bounded. Remember that we need here the Aronson necessary condition, but if f does not depend on the time, is the same to require that you have infinity regularity in time, and so the Aronson necessary condition became this condition. And this condition is the same condition that you need on the stationary problem to have bounded solution. So it is true that in this case, the difference of the solution go to zero in the infinity norm, or in other words, it's true that the solution of the evolution problem extends to the stationary problem associated to the parabolic problem. The result is true. Because it's possible to prove this estimate, they say exactly this. But what is really surprising is that this result remains true also if f is only an L1 function. This is rather surprising because if f is only an L1, u and w, the solution of the parabolic problem is not bounded. And also the solution of the elliptic problem is not bounded. We have also a problem of uniqueness, because if you have only L1 data, the solution is not unique. So I have to specify which solution I take here. I take here the solution obtained by approximation, because this is a unique solution in case of irregular data. So what is possible to prove is that if f is only in L1, the unique solution of this problem obtained by approximation tends in the L infinity norm to the unique solution obtained by approximation of this problem. I think that in a certain way this solves the problem, but only in this particular case when it's possible to associate to your evolution problem a stationary problem. But notice that in the general case that we are studying, if you have a dependence on t here, and the dependence on t in the operator, you don't have a stationary problem associated to your problem. And so what you can say in this more general framework? In this more general framework, something is possible to say, because you can consider a different elliptic problem, a stationary problem that is not equal to obviously to the parabolic problem. And you can try to estimate the difference of the forcing term here. Remember this I call G0. And you can also try to estimate the difference of the operator, the evolution and the elliptic case, calculated on the solution of the stationary problem. If you do this, remember these are these two functions, you have this result that we say, okay, the difference of this solution, the elliptic and the parabolic, can be estimated in terms of this quantity. Notice that this first term is a good term, because for t that goes to infinity, this term disappears. So if this function is in L1, also this term disappears when t goes to infinity. So this means that if the data f in the two different problems and the principal part are suitable proximate, suitable near, that means that this function here are in L1, then again you have that the solution of the parabolic problem tends to the solution of this different elliptic problem. But okay, can be a nice result, but that does not solve any problem, because maybe you are difficulty to find a proximate problem, a good stationary problem near to your problem. And what you can say in general, if you don't know anything about another elliptic problem near to your problem? I think that again, and I will finish with these results, again you can say something. What? Consider the same problem. Same right-hand side, so same forcing term, but different initial datum. You satisfy the problem with U0 as initial datum, and here I have a different initial condition. What is the relationship? What is the difference of behavior of this solution? It is possible to prove this result. If F is bounded, but here I can put also F satisfying the Aronson-Necessary condition. If F satisfies the Aronson-Necessary condition, this means that both the solution became immediately bounded, is the previous result. Then I can estimate the difference of these two solutions in terms of this quantity that says, okay, this means that for t that goes to infinity, this solution has exactly the same asymptotic behavior. Doesn't matter how is the initial datum. For t large, the solution has exactly the same behavior in L infinity norm. But what is really more surprising is that the same asymptotic behavior holds true also if F is only in L1. And again, this is surprising because if F is only in L1, this solution is not bounded. Also, this solution is not bounded because we need the Aronson-Necessary condition to have bounded solution. But the solution obtained by approximation of this problem that is unique and the unique solution obtained by approximation of this problem have this interesting problem. Their difference is bounded and is controlled in terms of this quantity that says that the behavior is exactly the same. In other words, it doesn't matter how regular is F, it doesn't matter how regular is U0. If you change the initial datum, all the solutions obtained by approximation of these problems have exactly the same asymptotic behavior, and this convergence is in L infinity norm. So I was really surprised by this result because they show us a lot of very interesting properties that are, if you have solutions that are not bounded, the difference is bounded. Moreover, this solution have the same asymptotic behavior. And finally, the solution immediately recovers the same regularity that would have for bounded initial datum. So thanks for the attention. I have finished.
Thank you so much, Maria Michaela. Thank you for this overview of all these results and this clear presentation. So now we have the time that we left behind to some questions or remarks. José Miguel Urbano already asked something to Nayan, and he already answered. Since only as the okay, and Sergey wants to. Okay, you can please go ahead, Sergey.
Can you hear me?
Yes.
Maria Michaela, congratulations, very nice talk. Well, I'm curious about one thing. You put in the condition, one of your conditions. What about the coercivity condition? You have U minus V square.
Yes, in that problem you have a strong monotony condition. You have that the operator calculated on a solution minus the operator calculated on another solution.
Yeah.
You want satisfy a monotony condition, a strong monotony condition with power 2.
This is, can this condition be improved? So instead of
Yes.
2 some p,
Yes.
so you should modify the exponents, but...
Yes, the result remains true also with power p when p is bigger than 2, but it's possible to prove the same kind of regularity, behavior, asymptotic behavior is, and also in case where you don't have this strong monotony condition, for example, for p less than 2, this is false, it's possible to prove that you have immediate regularization, but at the moment I am able to prove this for only for F sufficiently regular. I am not able to prove all the cases. But for the degenerate P-Laplacian is all the same. In the last case of less regular operator, you can find the same asymptotic, but not the strong regularization in some very not regular case. But I don't know, it's true.
But if P is greater than 2, that is...
Yes. There's another paper that I was accepted this year on Annali of Matematica Pura Applicata, and will appear in, I think, in these days, or maybe just is, if you like, I can send you the paper.
Well, I will be very grateful. Well, may I ask another question?
Okay.
One more. Well, the question is about the possibility of extending this kind of estimates to higher order derivatives. Well, high order, the first order derivatives, the gradient, the second derivatives, and so on. Because
I don't know, because I think that works for other kind of problem, more or less the same kind of problem for which I am able to prove the decay estimate. For example, also porous media, fast diffusion. I think that they are, and I am trying now to prove. For Haider, I don't know. I am not sure. I think that this will be a very interesting question.
Well, I'm asking because it's a well-known property, the high integrability of the gradient. So you start with some gradient in some LP space, and the integral over the cylinder will be in LP plus something.
Yeah, sure. I think that probably the result is true, but I will try. We can try.
I see.
It can be an interesting question.
Okay, and the very last question, and very quickly, I have to ask, do you have something of this sort, the result of this sort, to equations with variable exponent or non-standard growth?
I think that in this case, with if the exponent depends on x with good limitation, I think that more or less is all the same.
And if it depends on t?
If it depends on t, I think that is not so a problem, because I use integral inequality to prove this result.
Yeah.
So if you are able to handle the difference of two solutions, and it depends from the function that you put, I think that doesn't change. But we have to try. I don't know.
I see.
I expect that for good, it depends from which kind of function. Maybe it is interesting to try, because I think that the technique is very easy to use, to handle. So we have to try. I don't know.
I see. Thank you.
Expert for this. You and Erika.
Well,
Thank you. Yes. Thank you, Sergey. Well, we have other questions. So José Francisco asks Maria Michaela precisely, are the decay estimates also obtainable for solutions of quasi-linear parabolic equations beyond the Lorentzian framework, for instance, in Orlik-Sobolev spaces?
I think that maybe, but you in the Orlik means the right-hand side of the initial datum?
Oh, well, it was not written precisely.
But I think yes. I think yes, because what in the proof you use is what happens to the difference. So I think that maybe something can be proved. For F in the Orliks, for the initial datum, I have to understand. I am not sure. But if you put the right-hand side in the Orlik space, maybe something can do. But we have to, it's an interesting question for sure.
Yeah, okay. Another question, and now it's for Sergey. José Francisco is asking what happens if P is greater than 2?
Well, I expect that we can recover this range of exponents. For the moment, our limitation is purely technical. It's purely technical. But now well, recently we proved such a thing at the high integrability of the gradient. So you start from not very good initial data, instantly you have improvement of the gradient integrability. And so we can get rid of some technical unpleasant moments we have at this moment. You know, we claim that P is less than 2. And if I'm not mistaken, this was this is the same restriction you imposed in your work of 2006. Also, your power was strictly less than 2, and for the same reason. So I expect that for P, not much greater than 2, but greater than 2, we can recover the same results. That's what we are trying to do now.
Okay. I don't know if this answers you, José Francisco, because we cannot hear you. We just can read whatever you're written in this Q&A space. José Miguel Urbano was asking something to Nayan. He already asked, but I can share it with you. So the question was, what are the new tools? And okay, Nayan is here. Perhaps he would like to say something now that we can, all of us, communicate in person, right?
So I actually already wrote private tool, but I can say something. So I would say in the interior, the so-called expansion positivity is kind of a tool that is more flexible than weak hard neck inequality, because it's has a very strong measure theoretical. So basically it says the weak hard neck says if you have the pointwise estimate is going to be given by some sort of integral of the solution. So the expansion positivity is some weaker form of weak hard neck. It says the pointwise estimate can be obtained by the measure distribution of the positivity of the solution. So it's weaker. It's going to be more flexible to be improved, and that's the point of the interior. And on a boundary, on the other hand, on a boundary depends on which data you choose. If you handle Dirichlet data, it's the difference is there's no, you don't use expansion positivity or weak hard neck. The key point is to if you want to improve the iteration of your modulus estimate, you have to improve the sort of, it's very technical, it's hard to explain, but you have to improve the original technique of Di Giorgi in some sense, and make it the iteration go faster, and you improve the dependence in your estimate somehow. And for the Neumann problem, it goes back to, it can be attributed to the use of expansion positivity again. And so the improvement is the original paper of Di Benedetto also had this expansion positivity, but if you follow the original approach of Di Giorgi, you trace the dependence of the measure distribution of the positivity of the set, positivity of the solution is going to be exponential. Like the key point is to improve the expansion positivity so that it has a power-like dependence. Of course, this kind of power-like dependence also lead to a weak hard neck after finer analysis, but somehow I feel like it's more flexible to handle, like for example, the Neumann problem on the boundary.
So, and that meets precisely my question. So, in this work that you presented us today, you are deriving the result concerning the interior continuity of the solution, right, for the Stefan problem in the singular case, in the case that you can assure that the solutions are bounded, but you are also presenting the module of continuity, right?
Yes.
And what is precisely the role of the intrinsic scaling, and more than that, of the Harnack and of this expansion of positivity when deriving precisely the modulus of continuity? So
yeah, so this is the key point. So the Benedetto's approach or Di Giorgi's approach always starts from alternatives according to measure distribution.
Right.
So you have two alternatives. Either the measure goes like this, or the measure goes like that. Eventually, they lead to some kind of point-wise estimate, which is going to give you a reduction of oscillation. So this is exactly what the measure of the expansion positivity is going to do. The point is, now for Stefan problem, the critical number for the de Giorgi type lemma is going to depend on the oscillation. This is different from the porous median equations case or the parabolic P-Laplacian case. There, well, this is very technical. If there, the critical number for the measure distribution to derive the point-wise estimate in the de Giorgi type lemma is going to be independent of the oscillation. But for the Stefan problem, it's going to depend on the oscillation. So it's very important to trace where it goes when you work with the second alternative. So the first alternative, it's going to be fine. The second alternative, this kind of dependence on the oscillation has to be traced when you apply the expansion positivity or the Wickard-Nack. So it depends on this kind of it depends on where it goes and how it's going to affect the final iteration of your oscillation and finally the form of your oscillation. So if you can improve the expansion positivity from exponential type dependence to a power-like dependence, then you got something new. You got some new modulus. If you can keep improving, you can keep improving your modulus.
Okay, okay. Thank you so much. Well, they are saying that we have only 3 minutes, and I would like to, well, there are several questions that I would like to do, but being that said, I would like to make a question to Nicolau, just to bring him for our conversation a little bit. You said that there was this competitive behavior regarding the diffusion and the advection. Did you expect the result from the start? So just looking for the competitivity behavior, was what you get was what you were expecting to have?
Well, when we compute the divergent, we split the advection term in two. One of this part is acts like a source term, so which depends on a power of the solution itself. Then we can look to classical results like Fujita's paper, and we expect that depending on the initial state, you can have a blow up at finite time or not. And the answer is if you have the classical answer is if you have a small condition initial to the initial state, then we have that solution are globally. It's basically what we have, and I believe that the initial state is large enough, we will have blow up, but we did prove this.
Okay.
Did not prove.
Okay, thank you, Nicolau. So I would like to thank you all once again. It was a really, really pleasure to have you, all of you, in this afternoon. I hope to see you soon in a more present context and in different kind of meeting, okay? I don't know if you want to say something, or otherwise I will just say goodbye and hope to see you soon.
Thanks to you too.
Thank you.
Well, thank you, Rika, for the
All right.
organization and invitation also. See you.
Okay. See you.
Yeah.
Thank you so much.
Okay, all the best to all of you.
Bye.
Bye,
Bye-bye.
bye.
Bye.